Take a look at your CFU packet 3.4, dealing more with our work with residuals and the least squared regression line. So number one, it says during March the average temperature was 46.4 degrees and Joan used 490 cubic feet of gas per day. Find the intercept of the residual, or find and interpret the residuals for this month. Use your least squared regression equation from CFU 3.3, which I've noted there, right there. The y hat equals 1425 minus 19.78. Now it's hard to see that decimal, but there is a decimal there. So first thing I need to do is, in order to find the residual, let me undo that again. It's kind of a habit of mine. So first thing we need to do in order to find the residual, remember that your residual is equal to your observed y minus your predicted y. Right? Well, right here, this 490 is our observed y. In order to get the predicted y, we're going to use the equation y hat 125 cubic feet minus 19.87x equation. And so what we need to do is find out what the prediction equation would predict the number of cubic feet of gas we would use when the temperature here is 46.4 degrees. So all we have to do is plug that into our equation. 1425 minus 19.87 times 46.4. So on your calculator, all you have to do, pull that out. You can see we have some stuff from the other day. I'll go to large screen so you can see. Just plug it in. 1425 minus 19.87 times 46.4. Enter that in and we get 503.032. So y hat equals 503.032. Now, since they at least give me 2 decimal places for the prediction, I might actually leave my decimal as 3 places here when calculating out my residual. So now, to do my residual, my observed y, 1490. My predicted y, minus 503.032 equals negative 13.032. So again, if you think about what residuals represent, if this is my predicted line, since I'm negative, my observed value is below by 13.032, or below my residual line. So my prediction line is predicting that we're going to use more gas, okay? Or you could say that we use less gas than what was predicted. So I like to always kind of talk about the line. So the line, in this case, predicted that Joan's place or home would use 13.032 cubic feet of gas per day more than that, whoops, flip those, how about that? Then that was actually observed. So the prediction line is telling us that we're going to use about 13 more cubic feet of gas than she actually used on a temperature of 46.4 degrees. All right, so now let's continue on with number 2. Number 2 is talk about the stock market. here it says, some people think the behavior of the stock market in January predicts its behavior for the rest of the year. Take the explanatory variable X to be the percent of change in the stock market index in January, and the response variable to be the change of index for the entire year. So I'm just going to kind of note that X is the change in percent in January, and Y hat is the predicted change in percent for the year. So to me, it's always important to be able to identify what X is and what Y hat is, so we know what those are. So now, we expect a positive correlation between X and Y because the change during January contributes to the full year change. Calculations from data for 18-year period gives us this summary data. So we're given the means of X, the mean of Y, the standard deviation of X and Y, and we're also given the correlation coefficient. As you can see, it was positive 0.596. So A says find the least squared regression line for predicting full year change from January change. Show your work. So in order to get this equation, right, Y hat equals A plus BX, we need to find the slope, then find the y-intercept. So you're going to find B first, then find A. How do we go about finding B? Well, as we saw from today's notes, B is simply found by taking the correlation coefficient, dividing it by the standard deviation of Y over the standard deviation of X. We think about that formula. Standard deviation is the measurement of variability. So, and slope is change of Y over change of X. So you're going to basically divide the variability of change, multiply it by the correlation coefficient because that's going to standardize it, and we will get our slope. So in our case, 0.596 times 15.35 over 36. So again, just grabbing these values are standard deviation of Y over standard deviation of X. So then I just need to plug that into my calculator, and if you trust me with my calculation, I get 1.707. Now that's B. So now I still need to find A. So to find A, the y-intercept will equal the mean of Y minus B times the mean of X. Basically, whoops, I just noticed here I forgot the X in the formula here, and some of you might be going, Mr. Parts, what's going on here? Anyway, what's happening here is how this formula right here in blue is derived is it's just taking this prior equation right over here and replacing X and Y with the mean of X and mean of Y, because those 2 points we know go through the equation. And then I'm just taking this BX and moving it over by subtraction so that A is all by itself. So now all I have to do is solve for A. I know that Y hat was, according to this, 9.07. Then we're subtracting my slope, 1.707, times the mean of X, 1.75. So you can plug that in your calculator and you get A to be 6.083. So now our equation, we just put it all together. Y hat equals my A value, 6.083, plus my slope, since it's positive, 1.707x. And we got the equation. All right, B says the mean change in January is 1.75%. Use your regression line to predict the change in the index in the year in which the index rises 1.75% in January. It says, why could you have given this result up to round off error without doing the calculation. Okay? So at first they ask you to find it, but then they say, why could you have done this without actually calculating it out? Well, first of all, I'll actually do the calculation, then explain why you wouldn't actually have to. So one of the things you could have done is said, all right, y hat equals 6.083 plus 1.707, and you're replacing x with 1.75. Okay? So if we plug this in our calculator and round it, we should get 9.07. Now here's the thing. The question becomes, why could you have done this without calculating it? Well, this is the mean of x. Mean of x should correspond to the mean of y, since the point mean of x, mean of y is on our regression equation. So you wouldn't actually have to calculate it out. So we should know that if I'm given the mean at 1.57%, that should correspond to the mean of y, which if you look up top here in our data, 9.07%. So that's just a nice little time saver if you remember that the mean of x and the mean of y go through the point. All right, let's flip to the back page. All right, so on the back page, it says, do heavier people burn more energy? So it says, below are the lean body mass and the resting metabolic rate for 12 women who were subjects in a study of dieting. Lean body mass given in kilograms is a person's weight, leaving out all fat. Metabolic rate in calories is burned per 24 hours. Is the rate in which the body consumes energy. Here are the data again. So my guess is this is a problem we did, and I remember us talking about this, I think when we were talking about correlation and scatter plots back in like 3.1 and 3.2. So it says, enter the data into your calculator and make a scatter plot. So take a minute, take out your calculator and add these data points in. I'm going to pause it and do the same. All right, so hopefully you've entered in all your data into your calculator like I have. So just again, just to show you here that I have it in here, stat, edit, and I have all my data here in list 1 and list 2. So it asks you to make a scatter plot. So second y equals, I'm going to turn on my calculator, turn it on, list 1, list 2, zoom 9. So I get a pretty decent picture of my graph. So we want to do this on our calculator, okay? And that's what we are doing here in part A. So if you wanted to here, it says make a, enter in your calculator, make a scatter plot. So now, normally if we were to sketch this by hand, and what I'm going to do right now, if you want to, go ahead and pause the video again and sketch this by hand, but I'll at least get you your scale going. I'm going to be breaking the graph in both directions. Because if I look at my mass here, my mass values are basically going from a low of about 33 or 30 to a high of about 55, just under 55. So I'm going to count by fives here starting at 30. And then going up, the rate looks like it's going from about 900 all the way up to, looks like a little bit, somewhere between, a little bit more than 1,400. I'm going to start here at 900, 1,000, 11, 12, 13, 14, 15. So go ahead again, after I finish writing this, pause the video and plot all your points and see if it matches up with mine. Because I'm going to plot them all, and then I'm going to start the recording again. So here I go. All right, as you come back to the video, you'll probably see this big flash with all my points graphed on it. So just to show you, as I pull up my back to my calculator here, you can start to see how my graph is somewhat matching. Looks like this point probably should have been shifted over just a little bit, but my graph should look fairly close to what I have here. So now what it's asking for you to do in part B is use your calculator and your regression function to add the line of best fit. So to do that, first of all, I have to go stat, calculate, number 8, that's the linear reg, a plus bx, and that's going to give me my slope and y-intercept. So looking at this, since they give it to me at least in tenths, I'm going to go out to the nearest tenth, or the nearest, I might even go out 3 decimal places for my slope, but my y-intercept, I might go out just 2. So my prediction equation I have is 201.2 plus 24.026x. And again, I want to define what my variables represent. Okay? So x is the mass of the woman. And y hat is the predicted metabolic rate. And over here, I forgot to put metabolic rate. Glad I caught that label there. So now I want to add this line of best fit to my graphing calculator and then estimate the sketch. So y hat. So in this particular case, I'm just going to type in the equation 201.2 plus 24.026x. Go ahead then and hit graph. That line should just go right through my data there. So you can see it's kind of going in between these points here. So I just want to kind of guesstimate where that is. So I know my line of best fit is kind of going through something like that. Now on this particular one, it didn't really ask you to sketch it by hand, but it's always kind of good practice. If I were truly graphing this line by hand, I would want to use the y-intercept and the mean of x, mean of y as my 2 points. I'm not doing it in this case because it's really just asking me to do it via my calculator. Plus this one would be a lot harder to do the y-intercept since I've broken my graph. Alright, so now we've done part B. Part C says explain in words what the slope of the regression line tells us. Alright, so first of all, slope is the number in front of x. So my slope, in our case, if I look up top there, was 24.026. So every increase in x, this is what y is going, or what y would be going up by our prediction. So we would say something to the effect that we would predict an increase in the metabolic rate of about 24.026, and now we need to find the units. So what are they talking about in this calories burned per 24 hours or calories burned per day? So calories per day for each additional, and then is it a pound? What are we talking about with the mass here? So it says lean mass given in kilograms. So for each additional 1 kilogram, of body mass. that's what we were talking about. All right, D, last problem for this packet. It says another woman has a lean body mass of 45 kilograms. What was her predicted metabolic rate? So this is just plugging it in right into the equation. 201.2 plus 24.026 times 45. So you can plug that value right into your calculator, and hopefully you get 1,282.4 calories, okay, per day. So we would just say a woman with a lean body mass of 45 kilograms would have a predicted metabolic rate of 1,282.4 calories per day. All right, excellent. That actually ends our video.